Well, I start off by saying good data are a matter of fact, but mechanisms are a matter of opinion. And so there are many opinions on the mechanism for the Fischer-Tropsch reaction. I'm going to talk about the kinetic isotope effect. If you look at the reactants, the heavier atom, in this case deuterium, should react slower if it is the reactant side that determines the kinetic isotope effect. If, on the other hand, you look at the transition state, then you would get an inverse isotope effect. The heavier atom would be the lower energy, and so you would get the deuterium reacting faster than hydrogen. And that's going to be the basis. The extent of the isotope effect is going to determine the bond angle. The parallel or the linear is the one that will have the highest isotope effect. At room temperature, this isotope effect is around 7. So the hydrogen under normal conditions would react about 7 times as fast. Pardon me. In order to do this with deuterium, we have to show there's no exchange. And we have done this with 5 deuterated alkanes with hydrogen under synthesis conditions. There are no exchange that's measurable. With the olefin, we get exchange, but it's 1 deuterium at a time. And so the exchange is limited to about 4 deuterium into the hydrogen in the olefin. So if we just concentrate on the per deuterated compound, we don't have to worry about hydrogen-deuterium exchange. We do have to worry about accumulation in the reactor. The first peak is the per deuterated compound. The second peak is the hydrogen. You see, for octane, most of the product we're making when we switch to D2 is the per deuterated compound. We go to decane. We have retention of decane in the reactor so that about equal amounts of deuterated and hydrogen decane. When we go to hexadecane, about 90% of the product that we collect during that day was made previously. And so we have to correct the product that's coming out for the retention. And so we're just concentrating on the per deuterated compound. And so in order to do deuterium, I think we've shown by adding C2 to C10 alcohol that once you form the carbon-carbon bond, it doesn't come apart. We've added olefins from C2 to C19, we get the same effect. So we don't have to worry about so-called cracking or carbon-carbon bond breaking to impact the results. Now, this is work we got that caused us to think that the oxygenate mechanism was the one that prevailed. It's a little complicated. What we have done is add carbon-14 in CO2. The reverse water gas shift is not a major factor, but it does occur to some extent. The only product we're looking here is what is coming from CO2. And if you look at CO at the bottom square, that is the activity of CO. The bottom line is how much activity with increasing carbon number you could get if the product came from CO, and that's the green line. The experimental is the red line, so we're getting much more carbon-14 in the product than what we can get if CO initiates and causes the chain to grow. And so some intermediate in the water gas shift is able to initiate at least the chain growth. And so this caused us to conclude that an oxygenate intermediate is more likely the source of initiating the chain growth. This went against what most people had accepted. Our version, in which we're abandoning now, of the Emmett-Stewart oxygenate was that it was a common intermediate for water-gas shift and Fischer-Tropsch, and it was a formate mechanism. Emmett and Stewart in the 1950s had a different oxygenate intermediate that they used, and so we're going to have to go back to this or something that resembles it. Now, the hydrogen-deuterium kinetic isotope effect for CO2 hydrogenation. This is with a high alpha iron catalyst, one that contains 5% potassium. On the left, you see the rate of CO2 conversion. When we have hydrogen, we switch to deuterium, the rate increases. So we have an inverse kinetic isotope effect for the hydrogenation of CO2. The ratio in this case is the stoichiometric ratio, 3 hydrogen, 1 CO2. And the inverse kinetic isotope effect is about 0.7. Now remember, the inverse isotope effect, you need to have energy difference in the transition state, or so that we're talking about what, to explain the inverse isotope effect, not the one on the left where you would expect to get the normal isotope effect. If we look at platinum promoted cobalt catalyst, we get a similar effect. We've done this for H2 to CO2 ratio of 3, 2, and 1. We get a similar kinetic isotope effect, which is XH over XD. It's roughly 0.8. More surprising, and the reason we have to abandon the formate mechanism, it can give us an overall inverse kinetic isotope effect, but we're getting the same kinetic isotope effect for the formation of each carbon in the chain. So we have to have an intermediate that keeps repeating with chain growth, and the formate will not let us do that. If this is a plot of the data for the 3 hydrogen ratio for CO2 over platinum and cobalt, we see that we get reasonable straight line, so that we would expect this if you have the same kinetic isotope effect for each step of the chain growth. If we look at the low alpha catalyst, again, we're running hydrogen CO ratio of 2. We're doing this at 2 conversion levels of roughly 20 and 40% for CO. In both cases, we get the inverse isotope effect of about 0.7. And again, we get it decreasing, but not as fast as with the cobalt. Whoops, going too fast. So this is CO conversion, the rate with carbon number. And so there definitely is an inverse isotope effect. The one problem we have is that it's smaller than what we might expect. We've done alcohol dehydration where you get a positive isotope effect. It is on the order of 2.5, which is what you would expect for a temperature of about 250. The isotope effect we're getting is smaller than that, and so it's explainable by having a bent bond rather than a straight bond, but you want to keep in mind it's smaller than what we would like it to be if it is a linear intermediate. Now, if the title said CO2, but we've also done this for CO, and we get similar result. This is CO hydrogenation over the platinum cobalt. The bottom line is with hydrogen, the red is with deuterium. Again, you get the inverse isotope effect. So not only with CO2, but with CO, you get the inverse isotope effect. And it extends up through at least carbon number 8. It becomes more and more difficult to determine this isotope effect as you go to higher carbon number because you have to correct for carbon-13, which is roughly 1.1% of the natural carbon. And when you get up to carbon number 10, the correction factor becomes large, so that it becomes more difficult. But at least up through C8, we're getting a consistent effect, hydrogenation of CO. There's a similar result with the high alpha iron as well as with the low alpha iron. The one problem that we still have to consider, the result is what you would expect. If the inverse isotope effect applies, you have hydrogenated less of the olefin in secondary reaction than what you would if you have hydrogen. This is opposite the normal isotope effect, but it could be due to concentration on the surface being different for hydrogen and deuterium. We have tried to measure this with platinum. We're still going back to measuring, with the cobalt catalyst. We will go back and try it again. The initial effort, we could not detect a significant difference between the amount of hydrogen and the amount of deuterium absorbed by gravimetric between 100 and 400 degrees centigrade. I say we still have to repeat this by a different method. We were using gravimetric and pushing the limits of the technique. That is the one thing that is still puzzling and has to be figured. But in a matter of opinion, for 15 years I've argued for the formate mechanism. If I last 15 more years, I'll be arguing against it since it's nice for overall conversion, but it can't explain the constant isotope effect as you increase carbon number. So it accounts for CO rate, but it doesn't account for carbon number distribution. And so what can we say about the accepted mechanism? Time limits me to 3. One is referred to Pettit. He did atmospheric conversion and reinvented the carbide mechanism, which Fisher had back in the 1920s or 30s. But our data is consistent only if one of these steps, for example, the formation of CH2, is rate limiting. The addition of H or D to carbon to CH to CH2, etc. One of those steps have to be rate limiting in order to have that step have a kinetic isotope effect. The isotope effect only shows up when you measure the rate in the rate limiting step. So you can't have the equilibrium between the different CH, CH2, CH3. It has to go, and one of them has to be rate limited. This is lifted from Low paper for methanation. It's similar. Again, you see lots of structures, you see a cyclic mechanism, but only if a step D to E or E to F is the only rate limiting step will you get the isotope effect. And it can be the inert isotope effect. It only provides information for that. This for Fischer-Tropsch is a similar mechanism. Metless, and it's quoted frequently. However, only the formation of CH2 gives you the required inverse isotope effect. If you look at the formation of A, the vinyl intermediate, that will have a normal kinetic isotope effect, so that the deuterium data could apply to the formation of CH2. rest of the cycle is inconsistent with an inverse kinetic isotope effect. So the mechanism that's shown there was deduced from the deuterium studies. We've shown those data were impacted by product accumulation. Not only was the data not ideal, but the data cannot be used to verify any of the steps within the reaction cycle other than the formation of CH2, as I see it. The ENO mechanism goes back to Emmett and Storch. This one, step A and C, and so it can have the kinetic isotope effect for every carbon number, provided the formation of the CHOH intermediate is the slow step. The combination of two of those to give you chain growth and elimination of water should have a normal isotope effect if it resembles dehydration of alcohol, because the dehydrogenation of alcohol has a normal kinetic isotope effect. And so step B cannot be the rate limiting step in this ENO mechanism. It must be the formation of the oxygenate intermediate. A third mechanism that's frequently cited is CO insertion mechanism. Again, CO insertion cannot give you a kinetic isotope effect of either kind for deuterium, only the hydrogenation to an intermediate. I also don't favor the CO insertion because the hydroformylation reaction is well established. It only adds one carbon, and then the chain growth stops. And so under normal hydroformylation conditions, Fischer-Tropsch does not occur. It's only adding one carbon and then stopping. But this mechanism could apply provided it's one of the hydrogenation steps to give you an OH and hydrogen intermediate that is shown at the bottom step. So what is the conclusion that we reach? There's definitely an inverse kinetic isotope effect. The inverse isotope effect eliminates many of the steps that you see in the cyclic reaction as being rate limited. But with the data we've accumulated so far, we're not able to throw out any of the mechanisms. Only we can limit which step in the mechanisms can be rate limiting. And it must be one that forms an intermediate which the deuterium structure is more stable than the hydrogen one, so that you get the more rapid rate with deuterium. Otherwise, we have to say deuterium is absorbed to a much, much greater extent than hydrogen. Our preliminary absorption work is not consistent with that, but we need to get more accurate data there. With that, I will stop.
Thank you very much. We have been discussing the mechanism for Fischer-Tropsch for 100 years. Maybe we'll continue for